It's October 2017, and this is episode 81 of the Unseen Podcast. This is your host, Paul Carr, and we have a special guest tonight to talk about the last year of Boyajian's star and all the fun things that have happened in regard to Boyajian's star, also known as KIC 8462852. And our special guest is from Nexus, which is, I'll let her explain what that is. From at Arizona State, Dr. Eva Bodman. Welcome, Eva.
Hello.
Tell us a little bit about yourself and your research.
So I am interested in dust, debris, and disks, and how all those things relate to the formation of exoplanet systems. So not just the planets, but also the architecture of the system. Okay. And you've been at Nexus for what, a year or two, or? I became a NASA postdoc last February, so a little less than a year. Okay, we'll call it a year. All right, and also with us tonight is Adam Smith.
Hey everyone, happy 2 years of WTF.
And also, don't be surprised if later on you hear Nick Nielsen chime in. He may be late, or he may not show up at all. Okay, now we're talking about last year, at about this time, Adam and I did a show on the first year since the WTF paper came out. WTF stands for Where's the Flux? And talking about this very strange light curve of the star that has become since known as Boyajian star. It's one of the stars that the Kepler Space Telescope was monitoring closely over about 4 years, and is no longer monitoring because of problems with the telescope. But in the last year, we've had a lot of new developments, and so rather than taking you all the way back to zero, I'd like to sort of focus on the last 12 months. And if you're interested in the basic education about what's going on with the star, on my blog at Disowned Sky at blogspot.com, I'll have a link in the show notes. I have something called Tabby Star for the Perplexed, which is about a year old, and which sort of lines up what the questions were. And also, Tabby had a really good video that she put out about the same time with doing a TED Talk, and you can watch that, and in 20 minutes you'll have the whole picture. So, in the last year, since Adam, by the way, that show is by far our most downloaded show. Just me and Adam talking about Tabby Star. And that in the last year, a lot has happened. One thing that happened was, we reported on this at the last show, but there had been a Kickstarter to fund telescope time to monitor the star. But at that time, we had nothing new to report. The star was pretty steady. And that lasted through the winter period, where they really couldn't monitor the star very well with those ground telescopes. They had to use Swift and other space telescopes to monitor it, and also some of the more high latitude observers and the American Association of Variable Star Observers, many of whom are not Americans, I should point out, also monitored the star through the winter period. And into this year, until the Kickstarter funded network could pick up sometime around April or so. Actually, by 1st of May, they were fully operational and monitoring. And then we had some interesting events. Adam, do you want to comment on what we saw?
Well, we've seen this year around 100 days of dipping from Tabby's star, beginning, as you say, in May this year, lasting right through the summer. And we've seen this, we haven't seen the big 15-20% dips that the Kepler Space Telescope saw. these dips that have been observed this summer have been around the 1-2% region, but very similar in shape, the same asymmetric shape that, of the light curve that Kepler saw. So we know that something is definitely blocking the light, the flux from this star. And as you said, there have been a raft of papers written and published this year about observations from Swift, as you say, Spitzer Space Telescope, point basically to dust, a certain kind of dust, circumstellar dust.
Now we should point out that there were 4 clear dips this summer.
Yep.
They were given names by the Kickstarter supporters, and they are in order: Elsie, Celeste, Skara Brae, and Angkor. So we seem to have moved on to a kind of like a ancient
Lost cities.
lost city sort of. Yeah.
That's what Tabby calls them.
Or abandoned cities. We know where Skara Brae and Angkor are, but those cities were. That seemed to be the new theme, and probably the fifth. If you see a fifth dip, who knows if we will or not? That will probably be some other lost city, and they were all about 1 or 2% in brightness, which is a lot. If you think about the total amount of energy that involves, it's a lot of energy, but not, as Adam pointed out, not nowhere near as big as the ones we saw. The last one was, to me, the most mysterious one. And Eva, if you have any ideas about this, I'd love to hear them. Was Skara Brae, the third one? It was almost perfectly symmetrical, and it lasted almost 20 days.
Yeah.
Okay.
And right in the middle of the dip, there was some weird activity in what the telescopes are measuring. I don't think it was a glitch. It was too big to be a glitch. The brightness went up and down very rapidly, and then returned to this perfect U shape, and then went back up. And the descent and the ascent was almost the same duration.
Like a planetary transit. The symmetry is reminiscent of a planetary transit.
But it didn't have that bottom that you'd expect in a planetary transit, right? It did. I mean,
no.
If a planet came across, you'd expect the brightness to go down very slightly, bottom out, and then wait, and then the planet exits, it goes back up again. So that one is one of those hard to explain dips. The other dips were a little bit more ragged. Although Angkor was fairly deep. Angkor went to about 2%. It was the last dip we've seen, and that was at the beginning of September, and we have not seen anything since. But here's the thing that's interesting: we are seeing apparently some brightening since the end, at least since the end of Angkor, possibly before in the data. So no one knows to make of that as far as I know, but I'm all ears. Eva, can you tell us what are these dips? What do we understand about these dips?
Not that much, but with the asymmetry, it's probably like clumpy dust clouds of some sort transiting. But other than that, like how they're formed, that's still active discussion.
Well, now, one thing that Tabby noted pretty early on, even right after, and by the way, I understand the paper about this is coming out before we all die of old age, but which could be any time now. But she mentioned that the dips were deeper in blue than they were in red.
Oh yeah. These dips have a color, a very obvious color when you plot the different bands together. The blue is about twice as deep as the red.
Right.
And the eye is about the same.
Yeah, and now, again, you're the dust expert, so tell me if I'm wrong here. If you have something that's much more deep dip in blue than red, that indicates fairly small particles, right?
That type of color you can match with like 0.1 to 0.5 micron radius dust. So actually a bit of a range.
Yeah, we don't really know how dense the dust is, right? I mean, it's could be, it could be fluffy or it could be pretty heavy, right? I mean, yeah, you tell me. I don't know.
The density of the grains is not quite as important to the color as just the overall size of the grain. That's to 0th order. The most important thing to deciding color is the size of the grain.
Right. We're going to talk about the Wyatt paper that came out in preprint quite recently later. I don't think I'm not sure it's been through peer review yet, but.
Yeah, it has.
Oh, it has? Okay.
Yeah, it's been accepted.
Okay. So it's been accepted. That's good to know. But in that paper, he calculates what they call the blowout radius, which is, blowout size, which is a grain smaller than this will get blown out of that, away from that star, very quickly because it's, the force of the radiation pressure is stronger than gravity, and he gets 2.3 microns with some pretty reasonable assumptions. So the question that makes it sound to me like the dust that's causing this dimming is being created just now, right when we're seeing it.
Yeah. The short-term dips is most definitely newly created dust because it has to be so much smaller. But the long-term dimming, which that paper was focusing on, has to stick around for a long time. So that's why that lower size limit was assumed.
Right.
So that wouldn't have any impact on like the short-term dips.
Yeah, we don't really have a good sense of the color of the long-term dimming, right? Because we just don't have those measurements.
Yeah, there was that one paper, Meng and all.
Oh yeah.
That they said it was nearly gray.
Right, but they didn't find. I mean, the UV was dimming a lot more than the red. Yeah. Right. I mean, do I have that up here? Let's see. Adam, do you have that paper handy? Right.
Meng et al. Paper.
The Meng et al. Paper, yeah. I think it was something like a factor of 4 in magnitude.
Yeah, roughly.
Between the Swift data. Now, Swift data is a little noisy, but between the Swift data and the R data, which I think is AVSO.
Yeah, they looked at the dimming rates over different wave bands and saw, as you say, it dipped about 4 times as much in the ultraviolet than it did in the infrared, and they saw no infrared excess, which is kind of significant because that's what we see with young dusty stars.
Yeah.
Is that right, Eva?
Doesn't that kind of Eva? Doesn't that kind of jump out at when you have these really young stellar objects? There's a lot of infrared excess.
Oh yeah, they tend to stick out in the infrared, and they also are usually contained to certain regions near where they were formed. The really young ones.
Yeah, and it was something like the millimeter wave telescope. You can see a lot of that dust. Now, what Tabby told me, and I have not and this is on record on one of the WoW Signal recordings that I did, is that, and I asked her right after the May dip, which has since been called Elsie, if there was anything interesting in infrared, and she said nothing exciting yet. There's non-committal, but so far no obvious big signal in infrared. But I
None
don't.
that I know of.
Yeah, and the Wyatt paper states that Neowise was on in that first dip and didn't see anything.
Yeah, it was just flat.
Yeah.
Yeah.
And also there were spectra taken, which only went into the near infrared, but they did not see any change in the spectrum, which is interesting. So there, it wasn't anything, it wasn't gas. Right.
Yeah, it wasn't gas. Dust doesn't really start showing interesting features until you get into like the mid to far infrared.
Right.
And no telescopes at the moment can do that.
Yeah, which is.
We're waiting for. Are we all waiting for JWST then?
Yep.
Yeah.
Yeah. Well, yeah. W first will only go into like the near infrared. So, and so we don't really have a lot of a lot of options. And JWC just got delayed again, so probably won't see anything if we're lucky to 2020. And even then, I would think that might be optimistic. Probably more like 2021, 2022. And any questions yet, Adam?
Yeah, we have a question on the YouTube chat by someone called Martin who's asking about the Simon paper. So a paper came out titled "Where is the Flux Going? Long-term photometric variability of Boyajian star." Data from the all-sky Tabetha supernovae, and another one confusingly called the All-Sky Automated Survey.
Right. Yeah, I'm familiar with it.
Yeah. So they looked at 800 days of survey data and 4,000 days of the other automated survey. And they found that the star steadily faded in brightness from late 2015 to right up to this year. And they saw a similar long-term, what they call secular dimming, what the Kepler Space Telescope saw. But they also identified two brightening episodes. You said earlier that it appears right now that the star's brightening. They identified super brightening that have happened over the last 11 years, which is interesting.
Yeah. Well, I kind of wondered where the brightening was, because, you just can't dim all the time and not wink out. Yeah. I mean, the dimming that Monte and Simon saw was pretty. I mean, that would have, that wouldn't last a century. The star would go away. So, at some point there had to be some brightening.
Yeah.
I think that's another piece of the puzzle, right? What do you think, Eva?
Yeah.
Yeah. Definitely another puzzle piece. We've been so focused on the dimming that like none of us have, like, as far as all the people I've talked to, no one has really like thought of anything that would cause temporary brightening like in that paper. So
I think that I was just going to say the new paper by Wyatt and his colleagues mentions that they would expect periods of brightening after dimming events.
Well, I mean,
clumps of dust.
Those like brightening events aren't really associated with like the major dips. They're just
yeah.
kind of happened. Like,
and they're slow, right? Yeah,
yeah,
and also the I'm still trying to figure out the Wyatt paper, frankly, but he's talking about
yeah, it's
a
long.
lot of thermal emission, which would be infrared. So I'm not sure. I still don't understand that, but maybe I just haven't read it carefully enough.
It says that the passage of dust clumps through pericenter, which is the closest point these clumps of dust pass to the star,
Yeah.
is predicted to cause infrared brightening lasting tens of days. That's what this
Which
new
makes
paper
sense.
says.
Yeah. I mean, it would warm up when it gets close to the star,
Mm-hmm.
and then that heat would make its way through the dust clump and radiate out.
Yeah, they've developed a model where a dust ring, possibly caused by comets, is on a highly elliptical orbit. And they think that what we see along our line of sight is the passage of clumps of this dust through what's called pericenter, its
Right.
closest.
Now,
to the
Eva, this
star.
is not a real young system, right? I mean, might be 1 billion years old. So,
Yeah.
So this isn't the usual sort of planetary formation process that we'd see, right? This is something different.
Yes. But there is a possible companion star. So when that gets close by, if there's any sort of leftover debris disk, that star would stir it up, and you can get like things thrown in towards the star, things that could create these rings of dust.
Mm-hmm.
We still don't have a definitive answer as to whether that red dwarf star is a companion star or not. Are we ever likely to get an answer? Can Gaia tell us?
I don't think Gaia has it on his source list. It's too dim.
It might be too dim for Gaia.
Yeah.
I'm not sure. But if we just keep checking on it every couple of years, if we see it moving around Death Star, then
take like 10 years or more for us to be able to say.
Yeah, it's many years, yeah.
Yeah.
But you only need a small amount of the orbit.
Yeah, we didn't even know that star existed until they did the Keck observations. So, which is probably true of an awful lot of small red stars that we just don't know they exist.
We got a provisional distance to Boyajian star this year from Gaia, which is good. It comes out at about 490 parsecs?
Well, that 1490 was the sorry, not 1490 light years was the original estimate from the Boyajian paper, and the Gaia estimate was the error bars were so large that it included that estimate. So we don't really know if it's closer or further than what was in the Boyajian paper.
It's certainly a significant distance away from us. It's not in the solar neighborhood.
Oh no, it's
way out across the galaxy.
Well, it's not across the galaxy, but it's more than 1,000 light years away, almost certainly.
Yeah. That's across the galaxy to me.
Yeah, well, the galaxy is about 100,000 light years, so it's about 1% of the galaxy. But
not that far.
Given that it's so far away, I've been really impressed with all of the observations that we've had this year. It's not easy. It's not easy to the photometric variability of any star, given that this particular star is so far away.
Yeah. Well, the star's about 4 times as bright as the sun, so you know, it's a bit brighter than average. And if when you go out and look at the night sky, well, at least around here in the suburbs where it's not very good, what you tend to see are bright stars like Vega and Antares, which are big bright stars, right? And Yeah, but with a telescope as good as Kepler, you're going to see stars that are a fair bit dimmer than Tabby's star. And they think they can do about 30 parts per million or so in photometry, which is really good compared to what you can do in the ground.
Mhm.
And that's that's good enough to see a lot of interesting activity. So, I mean, maybe someday ground-based telescopes will do close to that, but that's pretty good. Now we are expecting a Gaia data release next year.
Yeah.
And sometime around April, I believe, is what they're currently projecting, and they're already starting to write about it, and that should nail down the distance to the star better than we
Definitely.
have now, maybe quite a bit better. And then we can say, well, gosh, it should be that bright, or it shouldn't be that bright, or based on the spectral type and so on. Okay, now
Do you remember, Paul? Do you remember last year we talked about Brad Schaefer's paper?
Right.
And he argued that the Boyajian star has been dimming for the past century. And
Right.
there was a lot of controversy about whether this was happening or not. Some people said yes, some people said no.
Yeah, about every other Thursday, I think he's right.
Yeah.
I mean, his argument is pretty good. I mean, he went and looked at the standard stars and measured them and he's an expert in measuring off the dash plates, which is, there are not many people who are experts at that. Most of them are at Harvard. And he measured the standard stars and found that this is varying like 5 times more than a standard star.
Do you think we can say now that he is correct?
I don't know that. I think the problem with the old plates is that they're full of problems that that could creep in. But I'm not sure that, and the other plates don't seem to corroborate. But the problem probably what's happening is you get these kinds of short-term dimming episodes. So if you don't have a long enough, and we have a big gap in the Harvard plates where there's just nothing. If you're getting these kinds of episodes like what Monte and Simon saw, which last a few hundred days, and then you maybe get brightening, which what Simon saw recently, it might have been going up and down that whole time. It might just be sort of an average, so it'd be really hard to corroborate it with anything else. It might have dimmed. Schaefer saw a big dip in the early 20th century, which he wasn't sure was real. That may have been, and he didn't really consider it to be decisive. And then we have this big gap between the end of the Harvard plates and so there's a lot where we just don't have enough information, where really nobody was really doing photometry on the star, accurate photometry on the star. Now Wise did view the star. It was on some of the Palomar plates. I don't know if anybody's gone back to look at the Palomar plates, but there's only a couple of them. There's a few of them, not that many, and they were taken over relatively short distance in time. So it's possible we will never really know for sure what was going on in the 20th century, and that's just maybe the way it is.
Okay,
that's my opinion. I'm willing to listen to someone who's better informed than I am. I interviewed Schaefer twice about this, by the way, and I also interviewed Grinley, who was the Harvard boss of the Harvard Dash investigation, and they've done incredible work there, but they're dealing with some really difficult data. The okay, well, let's get into a little bit. We've already talked about the white paper a little bit. These dust disks. What puzzles me is now it's true we don't have what we don't have, which would be decisive, would be like the infrared measurements right after a big dip, right? They're really telling. Another thing we don't have yet is that the white paper predicts that surveys like TESS and Plato will see, which are coming up, haven't launched yet, coming up. TESS should launch next year. Progress.
Yeah.
TESS and Plato should see more stars like this. That's another. If this really is that kind of phenomenon, that they were just happen to be lined up, looking at near the periastron of this orbit for this clump of whatever it is. But it may be purely statistical that we didn't see it in Kepler and any other star, and we get more stars with a lot of surveys going on. We might see these kinds of dips, and hopefully we'll be able to point James Webb Space Telescope over there and as a target of opportunity, and see the excess. That would be decisive. I think it would. I would have decisive, but it would certainly be a huge step forward.
Definitely.
But we don't have that information right now. We have just these little dips and an old beat up space telescope that no longer can see into the far infrared, that didn't see anything in particular. Right?
Were you surprised, Eva, at that we only saw these 1 to 2% dips this year? I think when the star first began dipping back in May, everyone got really excited. People went crazy on Twitter.
Yep.
I think it was fantastic that calls for observations were issued on Twitter. That's kind of a historic event, never before happened. Really cool. But yeah, were you surprised that we didn't see 20% dip? Is it just one of those things?
I'm not all that surprised that we didn't see a huge dip, mainly because, like, if you look at the rest of the Kepler light curve, there's several small dips throughout,
right,
away from the larger ones. So I mean, they outnumber the really huge ones. So it would have been nice to see a huge dip, but
it would be
I'm
nice.
just glad it dipped at all.
Now we Eva, correct me if I'm wrong here. We have some ground-based telescopes that can see at about 8 microns wavelength. Could that help us? I mean, there's a little hole in the atmosphere, right, where you can see infrared. It's right around 8 Is it 8 microns? I'm thinking. Is there? Could that help us?
Maybe. I'm not familiar with those instruments, so I don't know their precision. So I mean, it might be Tabby Star could be below their seeing limit, so it might just be another upper limit situation.
That's oh yeah, okay, well, no, I don't have, I was going to memory there, and I apologize, I don't have anything I can point you to. I believe in Europe somewhere, or maybe it's on the Canary Islands, there's a mid-infrared telescope that there's a little gap where the atmosphere doesn't absorb that much IR, and you can sort of
the Liverpool telescope.
Is that the Liverpool telescope? I think you're right.
Yeah, it's on the Canary Islands, Tenerife.
Yeah. if people are wondering what I'm doing, I'm looking at the.
Can I ask sorry, can I ask the question that probably most of our audience want to know, and that's, is the alien megastructure hypothesis dead in the water?
Well, we can
That's kind of
never
an unfair
say
question.
100% because we can't predict what extraterrestrial intelligent life would do. But if we're thinking like, an opaque body, the fact that these recent dips have color to them kind of ruins that hypothesis.
Yeah, I agree with that. Yeah. I mean, the classic Dyson sphere where you're building these opaque, or swarm, where you're building these opaque structures that block the star's light. But, she's absolutely right. I mean, we'd have no idea what they, maybe any sufficiently advanced technologies is indistinguishable from nature.
Yeah.
In which case, we're just not going to figure this out anytime soon.
Do we to rule it out more? Do we have to if we see one of these big, like 20% dips, and we see the same difference in ultraviolet against infrared dimming, would that help rule it out, do you think? We could say then for certain that the big dips are circumstellar dust, not something else.
Yeah, it would definitely help say it's dust.
Yeah.
Yeah, but that question that arises, right? You've already addressed one aspect of this, was there could be a companion star that's raising hell with the debris disk and causing things to fly in towards the star. But as the source of the dust, it certainly looks like during the dips the dust is being generated anew, and it also looks to me like the long-term dimming at least has some color to it. So there's a lot of and dust certainly is what we know that can cause that. But what is the comet? I know you've written about comets before as a possible hypothesis. Mm-hmm. The kind of comets you're talking about are huge, aren't they? They're way bigger than we've ever seen before.
Yeah, they're really large, but their total mass is not, like, if you combine them all into one object again, it's not that big. Actually, the main reason why I didn't go down to smaller, more reasonable sized comets was just computation time. Because it would go up, like, every time I went down by a factor of 10 in radius and comet size, the number of comets went up by 10. So doing 7,000 comets just is.
I think you said in your paper that it would take a close group of around 30, 100 kilometer radius comets, or 310 kilometer radius comets. Is that about right?
That sounds about right.
Yeah.
All moving in some kind of co-orbiting, or essentially, right? We're having nearly the same orbit. Yeah.
Yeah, roughly the same orbit.
So that would be like broken up from a bigger body.
Yeah, it'd be like the sun-grazing comets in our solar system. Bigger object ripped apart by tidal forces.
Yeah, and something that Wyatt is to lean towards something that's coming very close to the star, like well within one astronomical unit, maybe even quite a bit closer, to get the kind of dust population.
Surprised me at first, but they're talking about this dust ring being somewhere between 0.1 and 0.6 AU.
Yeah.
1 AU being the distance between Earth and the Sun. That's close. That's much closer to the star than I would have thought, because the lack of infrared excess seems to me to indicate that it's likely to be cold dust. But then the Wyatt paper talks about how this dust might be optically thick, so it's not letting us see any of the infrared radiation that is there.
Eventually we should see it, but it might be delayed.
Yeah, well, that's why we need the James Webb Space Telescope. I don't think we have an instrument that's capable of seeing that kind of small infrared excess. So there may be infrared excess. We just don't know yet.
But he does mention that the WISE measurements of this, but of course the WISE measurements weren't made during the dips, so we don't really know.
Yeah.
But yeah, you're right. I mean, we don't really have the big infrared telescope that we need. Sensitive infrared telescope.
Some more about your paper. You wrote this paper now, 2 years ago? It's been out there since November 2015?
Yeah.
In the past 2 years, you've had people proposing alternative ideas, and some people have said that the Kepler light curves are not comet-like. Other people have said that they can identify exocomets in the light curve. People say that the amount of stuff is unphysical. It's just too much. It would require too many comets and too much. Well, how do you respond to that kind of criticism?
I am still favoring the comet model. Even though it does have a hard time explaining the long-term dimming. But it's flexible enough that I can definitely do all the short-term depths. But even if the comets aren't directly creating the dust, to have that much cometary material heading towards the star, there's probably debris and dust in the outer system that could also be occulting the star. Because
it's a bigger star, can we assume that it probably has a much bigger equivalent to our Oort cloud, and that there is much more stuff orbiting the star? Right. That makes sense. I mean, me personally, I'm 100% with you on the comet hypothesis.
If that material in the outer stellar system is clumping on enough to produce those kinds of big or in the long-term dimming, I mean, isn't that? Well, I mean, first of all, the transit probability is very low out there, but but let's say just we see the transit. The fact that it I mean, you're saying there may be two separate mechanisms. One is the comets, and one is something else.
Well, those comets have to come from the Oort cloud or something similar to the Kuiper belt, and if we're seeing that disk near edge on or slightly inclined actually, and so there's all that dust and stuff in the disk plane that could be going from the star, creating long-term dimming, and then things, dynamical instabilities in that outer disk could be what's throwing the comets in.
Okay, but we're seeing both dimming and brightening, which means there's a pretty low entropy in that outer disk. Right? I mean, there's clumping and going on and other kinds of interesting activity. A
collision happens.
We don't see in our own solar system.
Could we be seeing a kind of late heavy bombardment type event.
Similar, yeah. That could be it.
So planets are getting hammered by lots and lots of leftover material and creating a lot of dust.
The dust mechanism is probably less, things colliding with planets and more like the asteroids and other objects hitting each other and just kind of smashing each other to bits.
Oh, okay. So smaller objects hitting each other in considerably large numbers, right? I mean, one asteroid doesn't have that much dust in it, right? But if you had a lot of them, you could see that going on. So, yeah, and it is all. I mean, this system is probably only about 1 billion years old, right? So it's compared to the sun, it's quite young. To a young stellar object, it's quite old. It's sort of in that. I don't know. Do we have other stars like this where we studied the system, and maybe instead of seeing an edge on, we're seeing a face on, and we can get some idea of what the density is?
There's Fomalhaut, young star, that has an edge on. It has a number of dust rings around it. We know that. That's like I say, that's the young star. I don't think we've ever a main sequence, ordinary main sequence star. That's why this star's so weird. Well, as we've said earlier, that we're going to find similar stars with similar kind of dips, long-term and short-term dimming, as we go ahead and do other observations with space telescopes like TESS and Plato. I don't think they'd be common, but we'd certainly find some more. You think that we're going to, in the next 10 years?
Well, no.
I have a suspicion that in 10 years' time, we might look back and say, well, what was all the fuss about?
Well, that happens a lot, right? I mean, when gamma ray burst first happened, people were completely baffled, and we're still trying to sort out gamma ray bursts, but with a lot better idea of what they are. Same thing with pulsars, with lots of other new phenomena.
Active galactic nuclei.
Oh yeah, quasars were quite weird when they were first seen. I remember in the 70s going to a lecture on quasars. There's all this weird stuff about quasars, and we don't know why it's like that. Ben Bova even speculated they were alien spaceships coming towards us. And we were seeing their rocket plumes, redshifted a lot. Of course, Ben Bova was a science fiction writer, so he gets it. He got to speculate like that. Didn't have any grant money to rescue, but it's possible. Yeah, I mean it could, but every once in a while you come across something like just like when you find a bug in your code, right? You say, how could this possibly be? And then, a lot of lost sleep later, you find one misspelling deep in the heart of the thing that led you one way instead of the other. It's like that. It could be like that, but the fact that we'd never seen a light curve like that before certainly got a lot of people very excited. Mm-hmm. And Jason Wright wrote some very good sort of triage of what the possibilities are, and what things are plausible or more plausible. And as Eva pointed out, the whole alien thing, since we don't know what aliens are or what they do or why they would do it, we don't even know how to include them in the model, right? So it's kind of until we've ruled out every other possible kind of natural phenomenon, we got no really business even thinking about it, really.
No, we can't have aliens of the gaps. theories, can we?
Yeah, well, that was.
Mhm.
Thank you for pointing out. That's one of my blog posts a couple of years ago. No aliens of the gaps. Aliens of the that we're almost certainly going to be wrong about are fine, but no aliens of the gap. And just
There is a theory. There's a theory that I mentioned when we talked about this last year that it's alien plankton orbiting the star, some kind of alien amoeba, or a growing colony that explains the long-term dimming. But
well, that would also show an infrared excess, I would expect. But the only alien thing I've ever seen that I thought was still plausible would be a very, very close in, made with materials that we have no idea how they would make it, mirror that's so close to the star that there's no infrared excess. It's about the same temperature as the star, and it's shining. And every once in a while we see some of that light blocked, but even that is there are problems with that. So it's not nobody's really come up with anything persuasive that I've seen, but which does not surprise me. If it is aliens, we almost certainly have no idea what we're talking about, and every hypothesis we come up with is going to be wrong. So that's I think we're we got to crawl before we can walk, and walk before we can run. So now I see we have another viewer. If you have any questions, either for Eva Bodman or for the whole panel, feel free. Adam is watching the chat, and if there's any more questions, we'll be happy to answer them. I'm also watching Twitter. You can tweet to at Podcast Unseen using hashtag EP81, and we will be happy to take your question or comment. It doesn't have to be a question. It can be, you can just, comment on my hat or whatever. We're a very informal podcast. Okay. So coming up in almost an hour. What's happened? Have we caught everything that happened in the last year? We mentioned the 4 dips. Never seen. Right now, we're not. It's been about 50 days since we saw a dip. There has been there was the Mung paper, the Simon paper, the Wyatt paper. There was also a paper on polarimetry, which I'm not sure constrained much. Somebody trying to sort of figure out the polarization of the light coming from the star. I frankly didn't quite understand the implications of that. I think the authors were pretty careful not to overstate it. But and then there was a recent paper which I have not really absorbed by Hipke and Angerhausen about the light curve is either asymmetric or aperiodic, which I have not really absorbed the implications of that yet. It looks to me like it's not periodic, but that's just we would expect if something is flying by the star and creating dust and then flying off into deep space and then coming back, that each time it's going to be different, because each time it's going to lose a lot of material, and it will leave behind material, which will move in a different part of the orbit, and so it might get more spread out. It might get the very, very sharp dip that was seen around day 800 in the Kepler data. A very clean, very sharp, slightly asymmetric dip that I've never seen that model very perfectly, but that dip seemed to look like something that was still very, very localized and then nothing, and there were no dips before. There were no really small dips that preceded it, or no really small dips that followed it. And then the next big dip had all kinds of mess going on around it. So that suggests that something evolved, right? Something changed over that time. And we don't know that.
I can't hear you anymore.
Can you hear me?
Okay.
All right. Sorry. We don't know that was a period of anything, but, you know, and we just don't have a continuous data set to say, yeah, this is periodic. So, you know.
Hip and Angerhausen said that the transits must have a period of more than 10 years or evolve significantly during a 4-year cycle.
Well, I think evolving is probably pretty likely.
Yeah.
Yeah, sure. There have been other papers written suggesting various periodicities. And there have been, so many papers written in the past 12 months, actually. I have trouble keeping up with them all.
There was one paper that was looking for a period that had 2 identical dips.
Oh yeah, I saw that. Yeah, the very, very small dips, right? Which they thought could have been a comet, right? Or
little comet family, yeah.
Yeah, but these are very, very small part of the total picture.
Yeah.
It was an interesting paper, but you know, intuitively you want to go for the one big explanation that explains everything. and then maybe there's 2 things going on, maybe there's 3 things going on. You know, people have been I know that Bruce Gary has been teasing a model. He's a retired astronomer who lives in Arizona and does a lot of really good photometry that involves brown dwarfs with enormous ring systems. And that's been brought up before. I don't think anybody's really published anything on that, but
there was that Ballesteros and et al. Paper that like mentioned a ring planet and then Trojans, but
yeah.
Oh, I remember that one. Yeah. That's true.
And nothing like that would complicated ring system to explain everything.
Yeah.
Not that I know of.
It involved really massive amounts of matter at the Trojan points, though. Which kind of raise questions. Maybe needs some follow up. But that did predict a pretty strongly periodic system, which, you know, we'll see. But right now we haven't seen that. Okay, well, do we have any more questions, Adam?
Yeah. Martin in the YouTube chat is asking about asteroid mining. Could we say anything about the possibility of lots of dust being created by alien asteroid miners?
Well, you know, that there was a paper about that by a couple of pretty respectable astrophysicists a few years ago, before Tabby Star was announced. Duncan Forgan and Martin Elvis. I've actually interviewed both of them on the WOW signal. And what they were looking at, though, was a much smaller scale thing. I don't think anybody's really modeled that. What they were hoping was that maybe with James Webb Space Telescope, you could see a little evidence of that, but it would all look pretty natural. It would be hard to distinguish. But if you had multiple lines of evidence, you might be able to say, this is really interesting. Let's look at it more closely. But nothing of the big signal like Tabby Star. So I don't know if anybody's really said, well, gosh, you know, what if we just mined every damn asteroid in the system? Can we produce enough dust to do that? And you know, I think it's an interesting question. I think maybe you know, maybe Duncan should get out a sharper pencil and look at that. It's entirely possible that, they were looking, what they said was most asteroids aren't very useful. Most asteroids don't have that much good stuff in them. So you would very selectively pick asteroids to mine. And that's something that Martin Elvis has been saying for quite some time now, that the vast majority of the asteroids out there aren't very valuable. But there are some that have like some small percentage that are worthwhile. What we're looking at here would be, a lot of asteroids with that are just getting ripped to pieces. So the material, someone would have to be finding all that material helpful for some kind of construction project. And I think the hypothesis that should be put forth, and it's probably wrong, but if we put it forth, we can figure out what observations we need to do to confirm it or disconfirm it.
Yeah.
But there was a good paper, and then I'll have a link to the show notes. But it was looking for a much lower level of asteroid mining.
Right. I got in touch with Mark Wyatt, who's written the latest paper, just asking him a few questions. I asked him about the difference between the long-term and the short-term dimming. And he said that it's probably due to different size dust particles. He says that the long-term dimming probably originates in gravitationally bound dust from perhaps exocomets, from a larger grain of dust, to the short-term dips, which are probably smaller particles of dust. And I think that he goes into some detail in his paper about that.
Yes, he does.
I also asked him, I also asked him whether his model that has this dust on an eccentric, well, not eccentric, elliptical orbit.
That's eccentric, yeah.
Eccentric.
Yeah, okay. Yeah. I asked him whether this rules out more complex scenarios that might involve a ringed planet, or, like you said, Bruce, Gary's developing a model with, I think, a ringed brown dwarf, or a dust being blown off the surface of planets, something like that. And he said that you can have a more complex scenario, which would have dust on multiple orbits, because this model he's developed just has all the dust on one single orbit. You could have a scenario where there are multiple dust rings, but that idea is disfavored, he says, because you'd have to have more material in orbit around the star, and that would break the infrared fact that we don't see an infrared excess.
Yeah. And then, of course, I did look at the Hill spheres, and it turns out that at reasonable distances from the star, a brown dwarf would have a pretty big Hill sphere, big enough to have a ring system that could occult the star significantly. But the ring system would have to be oriented so that in just the right way relative to how we were seeing it. I mean, I'm not going to rule it out, but I want to see how they make that model work. It's complicated.
That's pretty much what Mark Wyatt said.
Yeah.
He said that we should assume that we're not we don't have such a special vantage point along our line of sight where we see more than 2 or 3 orbits. We'd have to have a very special line of sight to see stuff on more than one orbit.
Well, but a special line of sight might explain why we haven't seen this in any of the other Kepler data, right? So it might be that the geometry is just right. It can't be perfect, but it could be, as long as it can be close to perfect, and still produce it, then that's, it can't be measure zero, but
Yeah.
it has to be something a little bit bigger than that. But but if that would explain why why this is so rare.
Yeah.
And
I also asked him what kind of observations he'd like to see in the future. And he said that he'd like to see ALMA, the radio telescope array, take another look. I know ALMA's been used already to look at this star, and they didn't detect a sub-millimeter excess, which we might expect of dust.
Well, that wasn't ALMA. That was actually the Hawaii telescope.
All right.
Oh.
But for ALMA's down in Chile, so the star only comes up a little bit over the horizon.
Oh, yeah.
Yeah. So
That's unfortunate.
because Tabby star is at 44 degrees north, right? So
All right.
it's not exactly circumpolar down in Chile. So they can see it, but it just comes up for a short time, then comes down. So it would be a pretty complicated observing campaign to observe it with ALMA. ALMA is the best instrument for that right now, but we need a northern hemisphere ALMA. Which
the other good instrument that we have is the Hubble Space Telescope.
Right.
Is that any use?
Well, as you know, Tabby and her team put together a proposal this year for Hubble, both as a target of opportunity and for a regular observing campaign, and they were turned down. They have learned from that and are going to resubmit.
Doesn't surprise me.
They're going to resubmit. They had good comments from the review board, and they are going to hopefully learn from that and resubmit, and maybe get some time next year. If Hubble lasts that long. Hubble's way past its warranty, so
yeah.
Writing a proposal to use the Hubble Space Telescope must be an art form in itself.
Oh, I think it's true for all the big instruments.
Oh yeah.
Yeah.
It'd be nice to get some interferometry time at Keck too, but the people that sit on those boards and determine what's the priority for those instruments don't always, they have their own sense of what's important, and you have to have a really good proposal. And I back several years ago, I interviewed Jeff Marcy, and I asked, and he was doing a laser SETI experiment at Keck, and I said, "How did you get the Keck people to agree to this?" So I didn't tell them. I just put it on there, and whenever we were pointed at some interesting target, I did the laser SETI. I turned on the laser SETI instrument, and but that was because they were out looking for exoplanets, so they can get time to do that.
Yeah.
So that was, Tabby's up against a similar complication here that not everyone thinks this is all that important, and there has to be their priorities, and Hubble time is expensive. So getting Swift time has not been hard. Pardon?
It's in constant use, isn't it? The Hubble Space Telescope, and oversubscribed. There are many more people wanting to use it and get to use it.
Yeah, well, and it takes very sensitive measurements, which you'd think you'd want to use those on things that are really faint objects, or galaxies, things like that. And the Hubble Space Telescope, for example, on this recent neutron star merger that was detected, the Hubble swung over there and right away, because there's some important astrophysics. You can't argue with that, and they got some great images. They saw this optical counterpart to the gravitational wave. So and of course they weren't alone. Lots of other people were doing the same thing, but
quite a historic event for multi-messenger astronomy.
Yeah, and this is the sort of thing that's evolved, in the last 20 years or so. This sort of targeted opportunity with, like we detect a gamma ray burst, swing over there and see what's there, and it's and I think right now, if we had a big dip, there's no setup to get the Hubble Space Telescope onto it. If we had a 20% dip, something like that, but hopefully that will change next. That will change next year. Hopefully,
that would be a big shame.
Yeah.
But I mean, there are other telescopes that could get good measurements that would be on it. Like the Liverpool telescope. So it's
there's a huge group of astronomers that are willing to pitch in, like if they just happen to have telescope time. So a huge dip happened, a lot of people would be looking at it. But
and the May dip, a lot of people did chime in with some interesting information. And Jason Wright has a lot of influence over Swift and Spitzer, so he can kind of get he can get them to swing over once in a while. But those are instruments that are out of their warranty and have in the case of Spitzer, it no longer has its coolant, so it can't see the long wave infrared. It can only see the near infrared. And
NASA have put it up for sale, I hear.
What's that?
The Spitzer Space Telescope is going on sale.
Yeah. I've not heard that.
I'm tempted to start up my own Kickstarter.
Well, sometimes that does happen. Like WFirst was the intelligence community just had an extra telescope that they didn't need, and they said, NASA, would you like this gigantic mirror? And NASA said, yes, please. Of course, WFirst still cost millions of dollars to put together, but
what do you mean you don't want this telescope?
Well, the intelligence community spends money like that amounts of money that NASA will never see. So
it's scary.
It was like sitting in a basement.
Yeah, ridiculous.
We got the surplus thing. You want it? It's it's a big mirror. Well, but and by the way, WFirst is being run out of Goddard, which where I work. But so anyway, any other questions, Adam? We had a couple of good ones.
Did someone look at the star with the Chara interferometer? I don't know.
Oh, Tabby did use an interferometer last summer. I don't know what she used it for, but she did mention she was on Mount Wilson using the interferometer with one of her graduate students.
I haven't read anything about that. I don't know.
Yeah, I know she uses Chara, but I don't know if she looked at this particular star with it.
Yeah, I know I did spend some time at Mount Wilson this summer, but she hasn't. She's been not. I think she doesn't want to steal her students' thunder about what they observed, so she's letting them report that. And I'm hoping we'll have a lot more information over the next 2 or 3 months about what was seen during the dips of this last summer. The dips seem to have quieted down, so but we don't know that's going to stay that way. And there does seem to be some brightening going on right now. So hopefully the next 3 or 4 months, we'll see all that documented and some interesting information come out. That it was just sort of leaked out that the NEOWISE was was observing during the first dip. Didn't see anything. There will be, it'd be great to see all that stuff lined up. Here's what happened when, and here's what we saw in this, and this, spectral data and the infrared and photometry, all that. I know a lot of people that just eat, like myself, would just eat that up with a spoon. Hopefully,
yeah. Hopefully there'll be a short letter paper in the next couple months.
Yeah. And for people who are not familiar, Tabby does have a blog, and not every day, but 3 or 4 times a week, she'll put out an update on what the telescope network is seeing that's funded by the Kickstarters, and anything else that's going on. And she done a good job of public outreach, given all the other things she has to do. So that's good. And if things are really quieting down, then that'll be time to get the papers out. And I know she's gotten the first person actually, Eva, when I contacted Tabby, I asked her to recommend somebody because I know she was too busy to do this podcast. She recommended you, partly because you were 3 hours behind us, so this wouldn't be too late for you. Also because you're well versed on the subject. She also said, well, I have a grad student, but I think he's not going to be available, but it'd be great. So I might have a chat with him offline, and then we'll put that on the WoW signal. He's been very closely working with her on the pipeline for the photometry. Now, folks, if you're out there listening, we will have a lot of stuff in the show notes, including links to all the papers we've discussed. And also, if you really want to talk about this thing on a daily basis, you can come over to our subreddit, the KIC 8462852 subreddit. I'll have a link to that in the show notes. It's and you can come over there and chat all you want about the different phenomena. You can put your speculation out there and see what people think about it. You can ask your Eli 5 questions. You can, and we have a wiki that you can reference. And the wiki's not perfect, but yeah, come over and help us fix the wiki. Help us improve it. So anyway, I will just Adam, I'll let you have any last thoughts, and then I'll go to Eva, and then we'll wrap up.
I think we're at a point now where we definitely know that it's dust, right? And it's not dust in the interstellar medium in between that star and us. We're pretty certain that it's circumstellar dust around the star. So the obvious question is, what's creating the dust, and how best to model it? I like Eva's model of exocomets. Some people think it's improbable that we have this, we might be seeing this moving close group of comets, because we don't see things like that in our solar system right now. But I don't think that's to say that such a close group has never existed in our solar system. Perhaps that kind of thing did happen a couple of billion years ago. We don't know. And maybe as we carry on looking out at other stars in the galaxy, we'll see very similar stars in the future. And I'm pretty sure that this is something that we've got a good handle on, or a much better handle on now than we've had previously. And we are on the way to understanding what's going on. So I'm quite pleased. I've been really impressed this year with all of the observations we've seen from lots of different people. I've been really impressed with Tabby and her team. It's very easy to follow along with the observations. If you just follow Tabby on Twitter, you get to see the nightly observations from the telescopes in Tenerife, and where's the other one? I can't remember. The other side, your side of the Atlantic, I think. Yeah, so follow Tabby on Twitter, and within a day she posts the last night's observations and a couple of other theories we haven't had time to mention. There's the planet-eating hypothesis, the idea that the star's been munching on a planet, and we're actually seeing variability in the star, not in anything around it. Can we rule that one out, do you think? Is it too early? I thought it was a good idea, but I don't think it's right in this particular case. Maybe it's something we'll see. Maybe it's something we'll come across in another star. Yeah, it's, as I say, we're on the way, I think, to solving this mystery, but it's certainly not. It's just case closed. There's still a lot that we can learn about, and lots of modeling for people like Eva to do, I think, before we're, before we're through.
Okay. Well, Eva, any last thoughts tonight?
Tabby star is still, it's nearly as much of a mystery as when we first, since that first discovery paper, you know. But now that we're swimming in data, basically, hopefully we'll be able to figure out something more specific than dust.
Great. Okay. And Eva, thanks for joining us tonight. And it's having you here has added a lot of really good quality content to the show, besides me and Adam just go around in circles. So although Adam's done great. Thank you, Adam. So that's it. Again, our show notes are at unseenpodcast.com. This is episode 81. And we would like to hear from you. If you didn't get a chance to view live, that you can still ask questions. You can go to our blog at unseenpodcast.com and comment there, or you can come over to Google Plus and join us in the community. Or we have both a listeners community and a participants community. If you'd like to be on a panel for a future episode of Unseen Podcast, that would be great. You can be on a panel. You don't have to be an expert in anything. Just have to have good questions. And so we would welcome you, and go to unseenpodcast.com to find out how to do that. It's really not very complicated. And also, next week, we're going to have another show. Usually we space them 2 weeks apart, but I like to have a Halloween show every year. And so we're going to welcome back James Garrison, who's been gone a long time. Hopefully he'll be back. And also Mateusz Macias and maybe a couple other people. And we'll talk about urban legends. It should be fun. Every Halloween we talk about something weird and spooky and strange. So tune in for that. I will post the Watch Live link very soon. You can follow us on Twitter at Podcast Unseen. You can email us unseenpodcast@gmail.com. And, please engage with us. We like to engage with listeners. We like those who ask questions tonight. Thank you so much. Thank you, Adam. Thank you, Eva. It is still just barely the 20th of October, 2017. This is episode 81. This is your host, Paul Carr. Music is by DJ Spooky. Thank you and goodbye.